This is a joint work with dozen of my colleagues at Google, along with Minlan Yu of Harvard and Ramesh Govindan on USC. And it's my honor to present this work on behalf of this group on network hotspots. Traditionally, data center providers have tried to give the illusion of infinite and rather unconstrained network bandwidth to applications where the application wouldn't need to worry about how their tasks and components are placed in the data center, right? And this is achieved by various techniques at the DCN layer. They pretty much do this by topology and traffic engineering to make sure that network is not bottleneck. And at the Tor layer, this is achieved by over-provisioning the network so the network does not become bottleneck. However, what we observe in Google Data Center is that if you look at the distribution of Tor utilization, even though the median is relatively low, there are a bunch of Tors, a small number of Tors that have fairly high utilization, higher than 75% and all that, right? And because in these cases, almost all of the links of the Tor are concurrently hot, there isn't much that host-based congestion control and load balancing techniques can offer to solve the problem. You can think about this research as almost a landscape of hotspot type of research, where we start by characterizing why do these hotspots occur, present some measurements around them, and some interesting production incident that they have caused in Google through the past couple of years. We then quantify the impact of these hotspots to services, in particular to storage operations, to see how much performance, heat they might cause. And then lastly, we develop scheduling and placement techniques to work around these hotspots and deal with them. I'm going to spend a few minutes on each of these topics, but as you see, the topic is, we touch on several different things, so we have a lot of breadth, but we don't go too deep on each of them because of the time constraint. So why do these hotspots occur to begin with? There's a very intuitive explanation where if you look at the distribution of workload demand, as in how much network bandwidth workload in Google Data Center needs, whereas distribution of network supply per Tor, as in how much Tor bandwidth exists, both of these are very long-tailed, right? In this graph, we're showing the CDF of amount of bandwidth that is needed across workloads per unit of compute, and in the other one, we're showing the CDF of supply, Tor capacity. So intuitively, if we don't have network-aware scheduling and placement of applications and their components, there will be hotspot. There will be imbalance between demand and supply, basically causing these hotspots. But a more kind of like capacity-oriented explanation exists for this, where when capacity planner try to determine how much bandwidth to provision, it's super expensive to build a non-blocking network. So then, as a result, they're going to introduce some sort of oversolve factor that if you're putting 4 machines, or rather if you're putting 400G of uplink, you're not going to put 400G, 100 gig per second machines, you're going to put more than that. And you make certain forecasts in terms of what kind of workloads are going to run and how your network are going to be used over the life cycle of this Tor that you're deploying today in your production. And whenever those forecasts are violated in your production, you are going to start to see this hotspot. And basically, this could be on the demand side because your workloads have more inorganic growth, product-driven growth that you hadn't anticipated. For example, if you have videos running in your production, change of resolution of the video could cause more demand, right? Or efficiency projects reducing how much, CPU use per unit of byte that you ship. And then there's other reasons. The mix of workload might change. Your data center might suddenly become more IO intensive compared to what you saw when you were provisioning, et cetera, et cetera. And then on the supply side, the Tor uplink capacity is prone to both planned and unplanned outages, reducing the bandwidth that you have deployed, causing another sort of imbalance, as in there's less uplink capacity. Also, over the life cycle of this Tor in production, you are going to deploy faster machines, beefier, storage appliances that can push more bytes per unit of, computer storage, and they are also going to cause imbalance on the demand side, right? In the paper, we actually show some a specific example of how these imbalances get triggered in production, in Google production, and how they cause issues for applications. And then we also present a bunch of interesting incidents from the application point of view of how do these hotspots qualitatively and quantitatively impact application. I'm just going to describe one of these interesting incidents on the application side, where some of Google's large distributed systems, such as Colossus, which is our distributed file system, have built a mechanism to cope with long tail latency, right? In Colossus' case, whenever a file is written in production, in addition to the code chunks that are the actual data, Colossus writes a bunch of code chunks which can be used to recover from failures. So then what is very interesting is that if you are a user, you're a client reading particular data that is located in one of your storage servers, if this server is slow, right, has a storage congestion for that matter, this notion of degraded read is going to be triggered, which is going to read some of these code chunks, and those chunks can be read and used to recover from the missing data chunk. And what is interesting is that this mechanism is very effective if you have congestion on the storage or on the network on the server side. But if you have congestion on this client, Tor, or client machine for that matter, this is actually pouring more fuel to the fire, right? This is going to actually make the congestion worse because you're bringing more bytes into it, and even the latency of the application become worse, which is the exact opposite of what you wanted to get out of this kind of mechanism. And it took us some time in production to observe these incidents and actually build intuitions around what is going on. And this just shows that we really need a solution for this problem. Then with that, in the next section of the paper, we actually try to more systematically quantify the impact of hotspot to storage applications. And the way that we do this is that we create these kind of curves of, as a function of tors that are involved in that storage operation, what was the latency of the operation, right? And we do this for two types of storage operation. One is very simple file system read and write operation through Colossus or distributed file system. And the second is much more complex distributed database queries through a system called QuerySys. This is a system that basically reading data from storage servers, then uses another system called RAM-store. This is a distributed memory system that does shuffle. So basically, if you're doing aggregation, it reads data from the storage, write it into memory storage, do some other aggregation, read again, write again. There might be several stages in it, so it's a very complicated operations. So showing the result that we got for Colossus, basically what is really interesting, just the high-level takeaway is that what we observe is that reading from disk is actually not that sensitive to Tor utilization, whereas write is very sensitive. I'm just going to spend a few minutes on this graph. Basically, on the x-axis, we're showing Tor utilization, Tors that were involved in that read. And on the y-axis, a notion of latency inflation, which is really normalized latency of that operation with respect to the lowest value, right? So what you see is that the blue line, which shows the total latency of operation, is just slowly linearly increasing up to 90%, which is the knee of the curve, and is very radically the latency increased. And the green curve, which shows the network latency, was only like 20% of the total latency. So almost it doesn't matter at low utilization regime, but in the high utilization, it becomes something like 40% or something, right? If you compare this graph to the right graph, which is right into the HDD, these are very different. Green and blue almost growing together very similarly. So actually network latency is a dominant factor of end-to-end latency. And the reason for that is that the way that write works in our production is that write is actually buffered in battery-protected server memory side. So the flush into the disk is actually not on the critical path of operation. That's why like the write is so much more sensitive to the latency. We do the same kind of analysis for the QuerySys benchmark. We look at 7 different industrial, these are common benchmarks that almost capture any type of SQL-like query that you want to do, aggregation, materialize, flush, et cetera, et cetera. And what we observe is also interesting is that there is almost 2 classes of queries. Some of the queries are more sensitive and show like at around 75% utilization, their latency inflation become 1.5 compared to an unloaded network. Whereas some other group of queries, these groups are much more tolerant, and up to 90-95%, you don't get to the 1.5 latency inflation. And we tried to build some intuitions around why that is, and what we found was that, which is intuitive, is that as the query is more compute bound, as more amount of time is spent in the computation, you see less sensitivity to the network hotspot, right? So in this graph on the x-axis, we are showing a notion of what fraction of time of the worker was actually spent doing computation, like filtering, addition, whatever, aggregation, whereas divided by the total end-to-end time of that operation, that query, which might include reading from storage, doing the shuffle, and all that. So what you see is that, and then on the y-axis, we are showing what was the utilization, what was the latency inflation at 75% utilization. As at 75% utilization, how much latency increased compared to unloaded network, right? So what you see is that as the compute boundness, as the compute ratio increases, the hotspot inflation decreases, which is exactly what I was describing, that the more compute bound the query is, the less sensitive it's going to be to the hotspot. But at the end of the day, as I described, there is a threshold at which all of these queries, are sensitive. Like, you really don't want to cross that 90%, 95% thresholds. So we need a solution to address this hotspot problem. And that is exactly the next thing that we looked at. Because fundamentally, this is a hotspot problem, meaning your average Tor utilization in the data center is low, but you have a small fraction of Tors running hot. This shows that if you kind of incorporate network awareness in your scheduling systems that schedule jobs or place data in your data centers, they could balance the load better to reduce the chance of this hotspot occurring. And this is exactly what we went and implemented inside our data center. So we basically incorporated network balancing as a new objective for Borg, which is Google Job Scheduling System, and Colossus, which is Google Distributed File System. I am only going to talk about Borg in this presentation, but in the paper you can read about Colossus. One of the things that we were very cautious about was that these systems are complicated, right? There was a reason that this was not added day zero, because they have many different objectives already for CPU and RAM, load balancing, failure recovery, user constraint, et cetera, et cetera. So we wanted to make sure that adding network awareness doesn't cause regression in existing objectives. And what we implemented was two kind of capabilities. One was that when a Tor is hot, like in this example, Tor be running hot, when a new job shows up and this system is about to schedule it, we avoid landing network intensive jobs on that hot Tor, right? And the second, which is complementary to this capability, is that if a Tor becomes hot, we have this system migrate some of the existing network intensive tasks away from that Tor into colder Tors. Basically, we're trying to balance this load and make sure all the Tors are even and we don't cross that hotness threshold. What we saw is that we got really, really good result from this Hotspot-Aware placement. This graph in the top shows fraction of Tors that were hot, and after a rollout, we could pretty much shave off 90% of the problem. And on the right side, you can also see the improvement, up to 13% improvement in the query assist benchmark that I was describing. And also, we saw reduction in production incident that we used to have in our data centers. We don't get full coverage because we are not running this infrastructure still in some of our clusters or special, and we have some gap in telemetry and all that. So the remaining incidents are due to that, but we have managed to get a good cut. And the key, and we achieve all of these without actually causing regression in existing objective, which was one of our really main constraints when trying to solve this problem. And the key insight of why we could do that is twofolded. Basically, really the thing that we discovered was that there's ample flexibility in the scheduler to deal with hotspot because of two things. One is that the average utilization of Tors in our clusters is low, so there's so many options for the scheduler to bin pack and spread the network load, right? And the second thing is that, as I mentioned, we're just trying to bring the tail utilization down below 80%. So we're just trying to bend the tail. We're not trying to, and it's not an aggressive constraint to add. So there's still ample room to achieve this. So with that, I'm going to summarize and then take some questions. Pretty much, we show in this research that Tor hotspots are an important problem to be looked at, and they arise because of bandwidth demand-supply imbalance. And we show that they could severely impact application performance up to 2x latency increase in simple storage operations as well as complex storage operations. And how much kind of effect you see depends to the compute boundness of the nature of that query. And lastly, what we show is that even a best effort hotspot-aware placement like what we did to try to balance and spread the load in a best effort manner could massively give you good result, solve significant amount of the problem. There's a whole bunch of set of future directions that we would love to see community work on and contribute to. One of the first things is that, as I mentioned, this network awareness and hotspot awareness are best effort. We cannot make any guarantee that all the hotspots will be solved. In fact, if you look at my graph, 10% of hotspots still remains, right? So how do we add SLOs around this kind of system? And that is going to require much more than simple spreading and kind of feasibility checks and presumably even isolation mechanism to deal with noisy neighbors, right? The second is that we added hotspot awareness at the application, at the infrastructure layer in our scheduling system, but you could imagine incorporating this in the application control plane. And there's non-trivial trade-offs because the application knows what operation is happening, knows the SLOs and can do the right prioritization, right? But it's not going to be generic. And also if we have multiple applications doing so, how do we have them coordinate? What kind of framework do we develop for that kind of coordination? The same set of problem exists in ML workloads, even more complicated, and the same techniques of network-aware placement could be used to deal with faults that we are seeing that exist for ML. The other angle which is interesting is connecting placement and provisioning, meaning, as I mentioned, when you do your capacity planning, you introduce this oversub, right? Because you don't want to build a non-blocking switch. Know that you have network awareness. How do you leverage that to safely run the network hotter? And how hot can you run the network relying on your network awareness? And then how do capacity planners, when and by how much do they fix the mismatches between resources and do the capacity planning, right? With that, I'm happy to take any questions.